All right, so today we are going to be talking about component vectors. Component vectors are a good way to break down the normal vector into its components, its x and y components. This allows us to do math a little bit easier and allows us to see things that we might not have been able to see before. All right, so let's get rid of this and pull up our first vector. So this is the vector we are given. We're given this vector, and what we're going to do, the way this video is going to work is we are first going to look at it graphically, and then we'll look at it geometrically. So let's look at it graphically first. So we have our vector, and our vector is right here. This is our vector, and in order to look at it graphically, we need a good coordinate system. So let's go ahead and put a coordinate system. And normally the coordinate system would go right in the middle, but since our vector starts right here, we're going to put our origin right there. All right, so this is our coordinate system. As you can see, this vector has a length of that much, and it has a direction in that way. Vectors have to have a magnitude, a length, and a direction, and we would typically classify this direction with an angle, but we won't get into that right now. Okay, so how do we break this thing down into its component vectors? Well, a good way to think about this is if you were to shine a light down on top of the vector. So the light is right here. This is our light, and it's shining down onto the vector and creating a shadow onto the x-axis. So this is our component vector in the x direction. So this is in our x direction, and then we can find the component vector in the y direction by doing the same thing. We're going to shine a light where it casts a shadow onto the y-axis. And we are going to see that the component vector looks like that. Maybe not that ugly, but the things that you need to know is that the component vector in the x direction goes as far in the x direction as the vector does also in the x direction. So if we were to label the point, the point at the end of the vector, if we were to label this point, we would say that this point is 4, 3. So our component vectors should have a number equal in which direction it is looking at. So our component vector right here has the coordinates 4, because that's how far it goes in the x direction, and then 0. And in the y direction, it is going to be 0, and then how high it is, which is 3. So as you can see, these numbers match and these numbers match, which is what we're looking for. So that's good. That means if we add these two vectors together, we will get our final vector. All right, so let's look at some more problems. All right, so these are our additional problems that were our additional examples. Let's go ahead and see what this does. The first thing we should do is slap on a coordinate system. So these are our coordinate systems. Again, we are starting our vector at the origin in both of these scenarios. For this one, I'm not going to draw the light. You can just imagine the light, but I will go ahead and draw the vector in the x direction. So for this one, the vector in the x direction is actually negative. It is negative. It goes negative in the x direction. And in the y direction, it is still positive. So this vector, this y vector, has a positive 2, and the x direction, x component vector is negative 3. This is good to know when you start to add vectors together. It helps when you're starting to add vectors together. All right, so this vector over here, the one on the far right, you can see that its x component again is negative, It is negative. And the y component is also negative. All right. You say, Mr. LeBlanc, why did you draw the vector over on, not on the y-axis? Well, because vectors, and especially component vectors, have this really cool property. When you add them together, they equal the last vector, the original vector. And as you can see, this creates a triangle. So there's a triangle that is created when you do this. And not only is it a triangle, it is specifically a right triangle. And right triangles, we can then use SOHCAHTOA to find specific values, especially if we know the angle theta. All right, so let's move down. Let's see what else we have. All right, so this is some more examples. So for this one, we're going to add an element. Okay, so this vector right here, we're going to say is the displacement. This is the displacement. And the displacement, say we had a cat and it walked all the way over here, and that's where it's at now, right there. We can break up the displacement vector into these component vectors. Now, I didn't draw a coordinate plane for you here because it'll still give us what we need. All right, so our displacement vector in the x direction, again, we're sticking with this shadow idea. This is our displacement vector in the x direction. Our displacement vector in the x direction. And our displacement vector in the y direction looks like that. Okay, so these again make a right triangle. They make a right triangle, which you can find the values using SOHCAHTOA. For our next example, we are going to quickly just draw the x and y. I want you to do this with me. So for the x, it is going to look like that. For the y, it is going to go down. So this has a value of 2 in the x direction and a value of 1, 2, 3, 4, 5, 6, 7, 8. 2 and 8. This has a value of 2 and 8. And we saw before this had a value of 7 and 7. So this is 2 and negative 8. That is their magnitude. Okay, for our last example, we are going to do a quick SOHCAHTOA and be able to figure out what this is. So this is a common scenario in physics. We have our velocity vector. Now I'm going to say that our velocity is equal to 13 meters per second. 13 meters per second. So our velocity is equal to 13 meters per second, and we're trying to find out what the velocity is in the x direction and what the velocity is in the y direction. I went ahead and drew the vectors for you, and as you can see, I didn't have graph paper because this doesn't quite look as good with graph paper. You can't necessarily look at the units and say, okay, that's how it is. So if this is 13 meters per second, then we can use sine. We can say sine of 42 degrees is equal to our opposite. Again, our opposite is Vy divided by our hypotenuse, which is our original vector, 13 meters per second. All right, so we're going to multiply 13 meters per second on both sides. And this gives us 13 meters per second multiplied by sine of 42 degrees. It's equal to our velocity's y component vector. Okay, that ends up, when you plug that into your calculator, that ends up equaling 8.7 meters per second. 8.7 meters per second, so Vy is 8.7 meters per second. We can then try to find our Vx, and this time we are going to use cosine. So cosine of 42 degrees is equal to our adjacent, which is Vx, divided by our original velocity, our hypotenuse, 13 meters per second. So again, we're going to multiply 13 on both sides, and this gives us 13 meters per second multiplied by cosine of 42 degrees, which is equal to our our velocity in the x direction, which ends up being 9.66 meters per second. Okay, good. So we know that this is 9.66 meters per second, and that's everything. That allows us to then add to other vectors if we want, but this allows you to find the specific values of the component vectors in the x and y. Thank you for watching.